Hello everyone. In today's video, we are going to look into the executor memory. So executor memory is a very important parameter while doing the Spark Summit. And depending on the task, depending on the code, you decide on how many number of executor you want, how much of code you want to allocate to each executor, and how much of memory you want to allocate to each executor. So in this video, we'll be looking into how to decide on this parameter of the executor, on which scenario which of the parameter will be best, and what should be the optimum executor number or the memory structure of the executor. So there must be some parameter on which the exact number of executor cores and memory should be decided. So for our example, we are going to take around 7 node cluster. So I'll make this as a cluster sign. So 7 nodes. So I have 7 nodes, and for each node, what how much memory we are going to use? We are going to use 16 cores and 56 GB of memory, or RAM, you can say. Okay, okay, write it here, memory. So in our example, we are going to take the cluster which is having 7 nodes, and for each node we have 16 core and 56 GB of memory. So if we talk about the total number of, so what is the total number of cores and memory? So we can say, so the total cores in our system is now 16 into 7. Okay, so it comes around 112 cores, right? Now the other thing is total memory available. So total memory, we have assigned 56 GB for a single nodes, and there are 7 nodes, 56 into 7. So it comes out to be 392 GB of memory. So this is our total memory and the core configuration of our system, or of our cluster now. Fine, we'll keep it here. Now, for defining on the basis of the optimum way, or a kind of perfect way of assigning the executor memory, so there are generally three divisions on which we decide on the executor memory. The first we call is a fat executor. The second is thin executor, and the last one, which we call it as a optimal sized executor. So we have three division: a fat executor, a thin executor, and optimally designed executor. Fine. So fat is the extreme big one. Thin is the extreme less number of resource allocated, and the optimal is the middle of it. So we'll talk about each advantage and disadvantage, and we'll see in an example, like which with an example, like what should be the fat executor or the thin executor. Right. We'll keep it here now. So what is fat executor? Fat executor means the executor which too much of memory has been assigned to the executor. That is called the fat executor. So I'll move everything a bit up. So fat executor means something like you have your executor in this mode will have maximum of the resources available. For system purpose, we have to assign some core and some memory, like one core and one GB of the memory for the system purpose. So what we are going to do, reserved core and memory for OS, yarn, or Hadoop cluster. So for internal purpose, I'll reduce the sign size. So for internal purpose, what we are going to do, we are going to assign one core and 1 GB of memory. Fine. So now our system is left with how much of memory? How much of core first? So core per node is available. Core per node is now, and this reserve core and the memory, like one core and 1 GB of the memory reserved for the OS and yarn, is per node for each node. So for example, there are 7 node, then 7 core, and 7 GB of memory on in the total of a cluster will be reserved for the OS and yarn or Hadoop or internal process. Okay, so the core per node which is left now is 16 minus 1, and this comes out to be 15 cores, and memory available now for node. Okay, that I'm talking about the per node memory. So we are having 15 GB of memory, the 15 56 minus 1, and this is equal to 55 GB. Fine. So I'm just talking about the fat executor. I have taken an example of fat executor, and everything calculation I'm doing on the basis of fat executor. So this is fixed, and this is overall, this will be same for the fat, thin, and optimal. We will see at the later part of the video. So this is now memory which is left with us. Now, as I have mentioned, fat executor means the executor which is consuming, or into which we have allocated maximum number of memories and maximum number of cores also. So the fat executor, for each node we have 15 core, and we have around 55 GB of memory. So as it is a fat executor, then we will assign all this memory and core to one executor itself. So in this case, one executor will have all the memory of that node. So it will be 15 cores. So one executor will have 15 core of memory. As I'm talking about the fat executor, so I'm assigning the all the resources to it. And for one executor, we will be having 55 GB of memory. Fine. So now in each node, now you see, in this case, when we have assigned all the memory to a single executor, that means each node will have only one executor. So we can say that each node will have one executor. Now there are 7 node in our cluster, so there will be 7 executor in the cluster. Fine. So this is a fat executor example. We have allocated all the memory and core to a single executor. So we have removed one core and 1 GB of memory per node for our OS yarn Hadoop cluster. So now I'm talking about the each executor. So one executor will have 15 cores, one executor will have 55 GB of memory, as it is a fat executor, and accordingly each node will have only one executor. There are 7 nodes, and there will be a 7 executor in the cluster. I think this much is fine. So this will be the configuration of the fat executor. So when you do the Spark submit, and the parameter which you have to give is num executor, means how many number of executor you want to give, you want to assign, if we have considered the fat executor. And we'll also talk like why, in which scenario we will need a fat executor. There will be 7 executor. Then what should be the executor cores? So executor cores means number of core what we assign to a single executor. Okay, so for a single executor we are assigning 55 GB of memory. So we'll write, sorry, I'm talking about the core. So executor core is the number of cores assigned to a single executor. So we are assigning one executor 15 cores, so we can write here 15. Then there is another parameter for the executor is executor memory. So executor memory means how many memory or how much of memory you are assigning to a single executor. So for the single executor I'm assigning 55 GB. So I'll write it here 55. 55 GB. So this parameter you have to pass in the Spark submit to have the fat executor mode. Fine. So it's not a mode like any switch is there in the Spark. Mode means, just for our understanding, if you want a scenario of a fat executor, then you have to go into this way and assign the memory in this way, and this will be your numbers. If you are going with 7 node, 16 core, per node 16 core, and per node 56 GB of memory. So I have written here GM by mistake. So I'll make it GB. Now we'll talk about some of the advantage and disadvantage of fat executor first. So fat executor, now you can see that in fat executor, you have a single executor having maximum number of cores. In fact, all the cores. You have 15 cores to a single executor. And you know that for each core, one task is being assigned. And if there will be multiple tasks in a same executor, then multiple tasks can work parallelly. I mean to say that if you have multiple cores for an each executor, then multiple tasks inside the each executor can work parallelly, because for each task you need a one core. So in our case, one executor is 15 cores. That means 15 tasks can be run or can run parallelly in a single executor. So this will give a huge parallelism when you are applying in a fact executor mode. So I can tell that in the advantage, good parallelism will be there, and this is because large number of cores in single executor, so multiple tasks can run in parallel. Fine. So this is one of the advantage of fat executor. Okay, the other advantage will be, as a single executor is having a large number of memory, that means a single executor will be consuming, or it can work on large chunk of data. So if there is a large chunk of data allocated to a single executor, then there will be a less shuffling inside the Spark cluster, and that will overall improve the performance of your Spark application. Use or substantial amount of data, whose data is assigned to execute. Okay, so this is the advantage. If we talk about disadvantage of the having a fat executor, then we have a few points in that. The first is, there can be like if there are multiple cores in a single executor, as we have stated that, then there will be multiple tasks which will be running parallelly. But that a core can be underutilized if you have a scenario in which you don't have large number of data to be processed. If you don't have large number of data which you need to process parallelly, in that case most of your core will be not be utilized, means most of the tasks will not be initiated inside the executor. So eventually your cores will not be utilized properly. So I can say here, underutilization of system of cores. Okay. The second thing is, as a single executor is holding a large amount of data, so in this case, what will happen if an executor fails, then the huge amount of data will be dumped, and then again that recalculation means the failure will be a huge failure, and it will impact a substantial amount in your Spark application. So the fault tolerance will be less here, or we can say that system fault tolerance, the amount of tolerance will be less, as large amount of data is being assigned to a single executor. So this was about the advantage, disadvantage, and everything about the fat executor. Now the question is, in which scenario we'll go with the fat executor? So if you have a huge or substantial amount of data, in that scenario you can go to a fat executor. If you know that there will be multiple calculation and you need multiple tasks and a huge amount of data, in that case you can go to a fat executor. So fat executor, the scenario is huge amount of data which you want to process very fast. Now we'll move to the thin executor, and then at the end we'll talk about the optimum executor. So I'll talk about the thin executor this side. Now the thin executor is that kind of executor in which we assign very less number of resources. Like in fat executor, we have assigned all the number of resources, but or the all the resources which are available we have assigned to the executor. But in thin executor, we will assign minimum number of resources to a single executor, and accordingly we will calculate the number of executor, core of the executor, and memory of the executor. Fine. So this thing will remain same, like you will reserve one core and 1 GB of memory of each node to OS, Yarn, and Hadoop. So this will remain same. I'll copy it. So as it is a thin executor, so we are going to assign a single core to one executor, and accordingly we will calculate number of executor and the memory which are getting assigned to this executor. So if you do now one quick tips I want to give you. So if you are doing any Spark memory management, you are trying to tweak on the memory parameter of the Spark. The thing what you need to remember, the first thing is you have to focus on one thing. You have to stick or make one thing stable or static, and accordingly other things will revolve around that. Now, in this fat executor, we have done the number of core to each executor as a stable. Okay. And similarly, in thin executor, in the other way, we are going to assign or we are going to make the core a permanent or static for each executor, and accordingly the memory and the number of executor will be calculated. So one parameter need to be placed first, and then other parameter will be evolved around that. Now the one parameter which is going to be stable there or stick there, that depends on the scenario, your data volume, your application behavior, your kind of transformation complexity. So the business requirement, and accordingly you will make one parameter as a stick as a stable, and then accordingly the other parameter will evolve around that. So in this case what we are going to do, we are going to assign one executor one core. So now we have assigned one executor as one core. So there are around how many of core in each node? So we have 15 core. So each node will have how many executor? 15 executors. Fine. So if one node is having 15 executor and there are around 56 GB of memory, so memory for each executor will be 56, sorry 55, I have 55 divided by 15 executor, and that comes out, so this comes around 3.6, so I'll make it 3. So each, or I can say each executor in a node will be assigned 3 GB of memory. So now what we have now is one core for each executor. So 15 executor in a single node and 3 GB of memory assigned to a executor. So our parameter will be like this: executor. So number of executor means how many number of executor you want to be there in the cluster. So there will be around so in a single node, we have around 15 executor. So number of executor total will be 15 into 7, 105. So in the system, we'll have 105 executor. Then executor cores. So executor core means number of core you have assigned to the executor. So number of cores assigned to each executor I'm talking about. So because this parameter defines the parameter for each executor, and number of executor defined as number of executor in a cluster. So executor core will be, we have assigned one executor one core, so we'll give it one. Okay. Then memory, executor memory. So we'll give how much of memory assigned to a single executor. So we have taken out here 3G, means 3 GB. So in the thin executor with the same node and a configuration, we have around 105 executor, one executor core, and 3 GB of memory or 3G memory assigned to each executor. Fine. Now we'll look into the advantage and disadvantage of thin executor. So in this, you see number of executor has increased. Okay. Although there is only one core to each executor, that means one task will be assigned or one task will be initiated from one executor. So multiple executor will run parallelly, but inside the executor, the task will be less. There will be only one task, so there will be no parallelism around the inside the executor. But overall, in a cluster, there will be many parallel process. So if you have if there is a small chunks of data you want to run on a parallel fashion, on a small chunks of data, in that case, this kind of scenario, thin executor will be good. So I can say that parallel increase in parallel execution on small chunks of data, or we can say that on on lightweight weighted application. Okay, and that application means the data load on this. The other thing is, now in this thin executor, a single executor will have a less amount of data because a single executor is having 3 GB of memory. And in the fat one, we have around, this is spelling is wrong. So in the fat executor, we have around 55 GB of memory. So in thin executor, we have around only 3 GB of memory. That means less volume of data will be assigned or picked by a single executor. So if a single executor goes down, then the less amount of data will go down, and there will be a less, or there will be a good fault tolerance, because your overall application will be running with large amount of data in a small in executor. But in case of failure of a single executor or one or two executor, so then you will lose only very less amount of data during the transformation. Overall you are not going to lose, but during the transformation you will be losing. Then again, with the help of DAG, the transformation that behind the scene RTD will be created. So overall your application will be a bit slow, but you are not going to lose any data. Either you make a fat executor or you make thin executor. Depend only, the thing is, your processing time may be hit depending on which kind of executor you are using. So in the thin executor, if in case of fault, in case of fault, less amount of data will be lost by executor. So again, I'm saying lost means the data is lost. Sorry, so data is not lost from the application. So that means data is lost only for that particular, from that particular RDD DAG or that action which is being performed on that particular data. And that can be recreated, as we know. If you have seen my previous video, then you'll be knowing that with the help of DAG, that can be recreated, as already is have a very good fault tolerance, so that can be recreated. So this was about the thin executor, and now fat executor. So thin executor, if you have a lightweighted application, then you go for a thin executor. If you have a heavy loaded application with large number of data, huge number of data, that will be, then will have a fat executor. Now in middle lies the optimum executor. So what are the parameters we need to look into the optimum executor? That we are going to look into this example, what we are going to see now. Now we'll talk about the optimal executor. Okay. So for HDFS throughput, we have to assign some cores to an executor. Like I'm not talking about leaving the resources for like in application master, or for this OS. I told like this GB and this core will leave or reserve for particular process, particular thing. But in HDFS throughput, for an executor to perform, have a good executor HDFS throughput. So for each executor, the optimum number of task or optimum number of core should be assigned to the executor for a good HDFS throughput is around 3 to 5. So here we have around 3 to 5 cores to executor. So this will be our starting point, because we want to achieve a huge, very good HDFS throughput, and for that we'll make an executor which will have around or in the range of 3 to 5 of the code. So in our example, we'll assign 5 code to an executor, and from there the full story of the executor memory and number of executor will be in picture. As I have told you in middle of the video, that for the memory thing, you have to make one thing stable, you have to fix one thing, and from there you have to revolve around the other memory parameter. So we'll take a parameter of HDFS throughput, and according to the HDFS throughput from the Spark the documentation, 3 to 5 core to an executor is a optimum number of core for an executor to achieve a good HDFS throughput. And from there we'll assign that number of cores to an executor, and we'll calculate the other memory parameter. Now the other thing is memory overhead. So memory overhead, as we have studied in the Spark memory management in our previous video, you can see that in the Spark memory management, so we have something called memory overhead, and each executor should exclude some of the memory to the memory overhead. We'll see that how much we want to leave for this purpose when we will work on this example. Okay, so we have these four parameters. Mainly these four parameters you have to focus on having a or creating a optimal executor. The first thing is you have to leave for 1 GB and one core of the memory or the code per node for the OS, yarn, and HDFS process. Then for the application master, you have to leave 1 GB and one core per cluster for each cluster, not for each node, for a core overall cluster. For HDFS throughput, you need to have 3 to 5 core of cores to assign to a single executor, and some memory you have to, or some core you have to leave for the memory overhead. Okay, from there we will start our calculation. Now the first thing is you have to leave 1 GB for this OS and yarn. So this will be again be coming this one. It will be same for everyone. So I'll just paste it the same thing here. Fine. So we agreed on this thing for all the fat, thin, and the optimal. Now other thing is here we have to leave for the application master. So that will be for each cluster. So now we have total cores available. So what is the total cores available now? So for each node we have around 15 core, around, not that is a fixed number, 15 core, and we have around 7, we have 7 nodes in a cluster. So total cores in a cluster is 15 into 7, and this comes around 105. Okay, 105 cores. And total memory, so total memory will be around 55 of GB, which we have for each node. So 55 GB into 7 node, and this comes around 385, around 385 G. Fine. Now for this purpose, for application, I'll write it here. We are doing it for application master, AM. So for those of you who is facing difficulty in getting all these numbers, so many of numbers and so many of calculation, I would suggest that go through the previous video, look into the Spark architecture, look into the Spark component, understand what is the application master, how it works, what is the memory parameter, reserve memory or overhead memory, and then come to this video. Then it will makes more sense for you. Okay, now moving forward, so we have this much. So we'll reduce one core and 1 GB for this. So what will be the total core left? 105 minus 1, and this comes to 104 cores. Now total memory left, this comes around 385 minus 1, 386, sorry, 384 G. Fine. Now we'll talk about the SDFS throughput. So as we have discussed, for HDFS throughput, we need to have around 3 to 5 tasks per core. So in our case, what we, I'll write it here in the bracket. The optimum range is 3 to 5 cores per executor. Fine. Now for this, for our case, what I'm going to assign for one executor will make it around 5 cores. Fine. So total number of executor will be, so our total number of executor will be, so for one executor 5 core, so total core is was left was 104. So we'll have 104 divided by 5, and this comes around 20 executor. Okay, so our number of cores is now 20, and then okay, I'll increase the size. Okay, so let me take everything up. And here itself I'll write it here. And then we have got each executor 5 core, total executor 20 executor. And then we'll have memory, means executor memory. How much will be our executor? So executor memory will be total memory divided by number of executors. So total memory left is around 384 GB of memory, and divided by total number of executors. So we have 20 executor. So this will come around 19 GB of memory. So now, till now, by looking into this reserve thing, then application master, then HDFS throughput, we come to a conclusion that executor core is 5, total number of executor is 20, and executor memory is 19G. Okay. Now, one more thing is left, memory overhead, this parameter. So for memory overhead, we have to leave some resources for that. Okay. So if you go to my previous video where I have discussed about the Spark memory management, you will find that for memory overhead, there is a formula that's a maximum of 384 MB or 10% of the executor memory. Okay, so I'll write it here. Overhead memory. So overhead memory is max of 384 MB or 10% of executor memory. Okay. So the 10% of the executor memory for each node, it will come around, I'm taking it around 2 GB. Okay, so what is left? Left is around total number of memory which is left is around for the executor memory is 19 GB. So 10% will come around 1.9 GB. So I'll just make it a round off and I'll give it 2G. Okay, because this is also a round off of something. So it comes around 2G. So actual memory. Now the thing is executor memory. Now this becomes 19 minus 2, and this is 17 GB of memory. Okay. So now everything is now fixed. So number of executor is 20. Okay. Let me. Number of executor is 20. Then we have executor core. So executor core we have assigned 5 core, and then we have executor memory, and executor memory we have assigned 19, then minus 2, it comes out to 17G. So this is our optimum number of optimum parameter depending on this particular scenario, optimal executor. I have not looked into the application complexity or the data. Sometimes your data skewness will give some different thing, and that need to be resolved, or they need to be managed from the memory thing. So for the skewness also, I have a different video. You can go into that. So that can be also add up into it, but I don't want to make it more complex. So this is the most simplified way how you can look into the memory thing. See, obviously you can have multiple more things. You can go more into detail of that, but I think for most of the application, this will be sufficient. This will be more than what is required. So this is all about the memory parameter. I'll make it okay. You can take the screenshot of it and then you can study it later on. If you have any doubt, please ask the doubt, because that will make the subject more clear to you. Okay, so I'll suggest everyone to come up with the doubt, ask in the comment, ping me, reach out to me, and then we'll make this more better for you to understand. So let me just make it more in a readable fashion. Okay. So this is what we have for the executor memory, and this doesn't cover everything what is there in the Spark documentation or what Spark recommend, but it covers most of the things which is required for the most of the application. I hope you will be able to understand this. Reach out to me in case of any doubt. Thank you.